Suppose we wanted to evaluate this integral, and suppose we wanted to do it by our method of substitution by matching. First of all, you're going to have to go through these steps, which can look quite daunting, but as you practice more and more, the steps will start to flow better from one to the other, and it'll become second nature to you, but it does require lots of practice. Before we actually get started with this, let's copy the problem back down again. Now, because the general power rule for integration, which we'll be using eventually, doesn't deal with radicals, the very first thing I want to do here is change that square root to a 1/2 power, because that's what the general power rule for integration works with. It works with powers. So I'll rewrite that using a 1/2 power instead of a square root. Now let's start using the steps. The first step says to set u equal to the expression raised to the power. Now I'll say this, if you have any doubt about what you should choose for u, here's a little tip. For what we're doing now, and as you get used to this process, this tip will usually get you where you need to be. And that tip is, if you're in doubt, choose u to be the expression with the highest power. So if you look in this integral, there's an x minus 3, that's x to the first power. But down in the denominator, you've got an x squared minus 6x plus 1. That's a higher power. So my tip would say, choose that to be u. So I'll do that. Let u equal x squared minus 6x plus 1. Step 2 is to compute du dx. That's the derivative of u. That would be 2x minus 6. And our ultimate goal, which is what step 3 is to solve for du. So I'll multiply both sides by dx. The dx is on the left, divide out. And I end up with du equal to the quantity 2x minus 6 multiplied by dx. Now, another little tip, if you like, whenever you see a differential that has a common factor that can be factored out, most of the time you're going to want that factored out. So I'm going to take the common factor of 2 and factor it out of that and go ahead and write du as 2 times the quantity x minus 3 times dx. And you can probably see now why that was a good idea, because if you look back into the numerator of the integral, you'll see that x minus 3. And you can see the wisdom of factoring that 2 out here. In any case, step 4 now says if the integrand has a numeric constant factor, you can move it outside the integral. There is no numeric constant here, so we don't have to worry about it step 4 this time. So we can move right along to step 5. Step 5 says to reconstruct the integrand so that the u part is followed by the du part, remembering that we can compensate by a constant factor if needed. So the u part is the part associated with what I called u, including the exponent. So u is the quantity x squared minus 6x plus 1, and since it's raised to the 1/2 power, I'm going to include the 1/2 power as part of what I'll call the u part of the integrand. Once you do that, the rest of the integrand, the x minus 3 in the numerator and the dx differential, will be part of the du. I'll call that the du part. I want the du part to be at the end, and the x minus 3 is part of the du part, so I'm going to physically shove the x minus 3 out of the numerator over to multiply the dx. Now it's perfectly okay to do that, because that's like x minus 3 over 1, so you haven't really moved it from the numerator in theory. It's just pushed with the dx. But you cannot leave a numerator without anything in it, so I have to insert a 1 there. And you can see that doesn't change anything, because where you put the x minus 3 back up there, x minus 3 times 1 is just x minus 3, and you're back where you started. So I've manipulated this around so that it looks like step 5 said it should look. The u part is first, followed by the du part on the end. That's what number 5 says we should do. You can see already that because u is equal to the quantity x squared minus 6x plus 1, that's going to be the u substitution that step 6 talks about. But what about du? I can't do du yet, because if you look back down at the lower left, du is supposed to be 2 times the quantity x minus 3 times dx. But in fact, if you look back at what I've labeled the du part, there is no 2 there. The x minus 3 quantity is there times dx, but we're not seeing a 2. So that's where the part of number 5 that says that we can compensate by a constant factor if need be comes in. We're missing a 2 that we need in the differential looking in the lower left. We can insert that 2 only if we multiply by the reciprocal on the outside. The reciprocal of 2 is 1/2. Now what has happened? We already saw that the x squared minus 6x plus 1 is going to come out as a u in step number 6, but now the entire right-hand part is all du. So it in fact can come out, and now we're ready to do number 6, which says to substitute the u's and the du's. In other words, get rid of every x and every dx in the original problem and change them to u's and du's. And you can see it's already practically done for us. I'll copy it back down, and don't forget the 1/2. If you get carried away with all the integration, don't forget that constant 1/2. It has to stay in the problem. But back to the substitution on the integration. The x squared minus 6x plus 1 becomes the u, and it's raised to the 1/2 power, and it's 1 over u to the 1/2 power. But everything else following gets absorbed into the du. Look very closely at this, because if you don't understand how the substitution worked, anything you do after that is just wasted time, because you're not going to be able to reproduce that consistently if you don't understand what just happened. So the setup in number 5 that allows step 6 to successfully take place is a key step here, and you've got to think it through and make sure you've got it. Very important, getting from step 5 to step 6. Because once you do this, you're practically home free. The one thing I would warn you about is that the general power rule for integration tells you how to take the integral of u to a power, but this is 1 over u to a power, so we need to do something about that. But luckily, we know that 1 over something to a power is that thing to a negative power. So in other words, 1 over u to the 1/2 is simply u to the minus 1/2. Now it looks like something that the general power rule for integration can take care of. As you keep working, do not drop that 1/2. You're not doing anything with it, but you need to keep carrying it along. The general power rule for integration tells you how to integrate u to the minus 1/2. And as you see, what it basically says is if you start off with u to a power that you want to integrate, you end up with 1 higher power. So we're going to have to figure out what is 1 more than minus 1/2. Minus 1/2 plus 1 is going to be a half, because 1 is 2 halves, and minus 1/2 plus 2 halves is 1/2. So the power on u is going to be 1/2, but the formula also says that you have to multiply by 1 over that new power. So we have to multiply by 1 over 1/2. And that just means the reciprocal of 1/2. 1 over a fraction just flips it. So 1 over a half is 2. In other words, the reciprocal of 1/2 is 2. Don't forget that. And also don't forget this is an indefinite integral, so you have to put plus c. Now it's a matter of just tidying up the arithmetic and getting rid of the u's. 1/2 times 2 is just 1, so we end up with u to the 1/2 plus c. And the u's were what we put in there. They weren't in the original problem, so we have to get rid of them. But we're also running out of room at the bottom, so I'm going to take that u to the 1/2 plus c and write it up top and continue from there. Step 8 says, the final step, substitute the x values back in. So u is the quantity x squared minus 6x plus 1, so we substitute it back in, and there you go. And keep in mind, if you have any doubt that you got the answer right, all you have to do is take the derivative of what I've just boxed in there and convince yourself when you take its derivative, you get what you started with. You can always check these integrals by differentiating and see if you get what you started with. So if you end up with that answer, differentiate it and see if you get back the integrand that you started with. If you do, you know you got your integral right. In any case, there's your answer.